Mechanics is a branch of physics which studies motion and how it relates to applied forces. It is usually divided into three parts: statics, kinematics, and dynamics. Statics is the study of equilibrium and its relation to forces. Kinematics deals with the mathematical description of the motion of objects without considering what causes motion. Dynamics, on the other hand, studies the causes of motion and how they affect motion. In this lecture, we'll focus on the kinematics of particles, where a particle is a body of negligible size and internal structure. So when considering a particle, we assume all the mass is concentrated at one point in space. We can define motion as the change in position of an object with respect to its surroundings at a given interval of time. We have many different types of motion, and some of them include translational motion, random motion, oscillatory motion, and rotational motion. Now let's quickly define and explain some key terms that will be used throughout this video. Distance. Distance measures the length between objects or points without regard for direction. Distance is considered a scalar quantity. Displacement is the measure of an object's change in position from an initial starting point to an ending point with regard to the direction of its travel. Now let's illustrate the difference between distance and displacement by considering 2 points A and B. If we take the path P in moving from A to B, the distance covered is taken as the length of path P. It is a scalar as it has only magnitude. The displacement of point B from point A, on the other hand, has a magnitude equal to the length of a straight line connecting A and B, and its direction is the direction of line AB. It is a vector because it has both magnitude and direction. Speed is a scalar quantity which can be defined as rate of change of distance with respect to time. Velocity, on the other hand, is a vector quantity defined as the rate of change of displacement with respect to time. And finally, acceleration is defined as the rate of change of velocity with respect to time. Let's now consider the simple case of motion in one dimension, which is in essence motion in a straight line. This type of motion is also called rectilinear motion. So we use the variable x to represent displacement, v for velocity, and a for acceleration. For simplicity, I'm going to remove the arrows since we know we're working with vector quantities. Now let's derive the equations of motion, which we can use to solve problems involving motion in a straight line. These equations we're about to derive only apply to motion with constant acceleration. Recall our definition of acceleration, where we mentioned that it is rate of change of velocity with respect to time. Mathematically, we can write that as A equals dv over dt. Rearranging this, we get dv equals A dt. Now we put our integral signs. So for this, we want to use definite integral. We're going to be integrating from an initial time t equals 0, where our initial velocity can be written as v0, to a time t with a corresponding velocity v, which is unknown. Thus, our integral becomes the integral of dv from v to v0 equals the integral of a dt from t to 0. Integrating this, we get v from v to v0 equals at from t to 0. And then we can solve by substituting, and we get v equals v naught plus at. This is our first equation of motion, which establishes a relationship between our instantaneous velocity, the initial velocity, the acceleration, and the time elapsed. Now, to derive our second equation of motion, we can also denote our definition of velocity mathematically as v equals dx over dt, where x is our displacement. Rearranging this like we did previously, we get the integral of dx equals v dt. Now, substituting our first equation of motion for v, we get the integral of dx equals v naught plus at dt. Now, still using definite integrals, we integrate from an initial time t equals 0, where the displacement of the particle is also 0, to a time t where the displacement x is unknown. Our integrals become the integral of dx from x to 0 equals the integral of v naught plus at from t to 0. Integrating, we get x from x to 0 equals v naught times t plus a t square over 2 from t to 0. Now, solving by substitution, we get x equals v naught times t plus half a t square. This is our second equation of motion, which shows a relationship between the displacement of a particle, its initial velocity, its acceleration, and the time elapsed. To derive our third equation, let's take our equation 1, which is v equals v naught plus at, and square it. So when we square both sides, we get v square equals v naught square plus 2v naught at plus a squared t square. If we factorize out 2a from 2v naught at plus a squared t square, we get v square equals v naught square plus 2a into v naught times t plus half a t square. If you recall from our second equation of motion, v naught times t plus half a t square is equal to our displacement x. So that means we can substitute that into this expression, and we get v square equals v naught square plus 2ax. This is our third equation of motion, which shows the relationship between the instantaneous velocity, the initial velocity, the acceleration, and the displacement of the particle. Now, let's do a quick recap to remind us of all the equations that we've derived. Our first equation, v equals v naught plus at. Our second equation, x equals v naught t plus half at squared. And lastly, our third equation, v squared equals v naught squared plus 2ax. We are now going to consider the special case of freely falling bodies, which is a type of one-dimensional motion. Here, we study particles falling under the influence of the Earth's gravitational attraction. It has been experimentally determined that all bodies at a location fall with the same downward acceleration, regardless of their size or weight. And this acceleration is called acceleration due to gravity. It has an approximate magnitude of 9.80 meters per second squared. Now, since our acceleration is constant, we can also apply our three equations of motion to freely falling bodies and write them as such. V is equal to v naught plus gt, y equals v naught times t plus half gt squared, and finally v squared equals v naught plus 2gy. We use the variables y and g to represent displacement and acceleration, respectively, because we are dealing with vertical motion under gravity. Now, since the acceleration due to gravity is always downward, any motion in the downward direction is in the direction of acceleration due to gravity, and hence its acceleration is positive. Likewise, any motion upward is taken to have negative acceleration. Thus, we can write the equations for downward motion and upward motion separately. Now, as you can see, the equations for downward motion have positive signs because they have a positive acceleration, while the equations for upward motion have negative signs because they have negative acceleration.